Okay, so we have been introduced to log functions now, and now we're going to look at a few rules that go with them to make them easier to work with. So the first thing that we want to remember is that logs are very similar to exponents, and so logs and exponential functions are actually inverse functions of each other, and so the properties of exponents and the properties of logs are very similar. Okay, so the first thing, I'm just going to use, for the most part, a generic base b or ln in this case. The base could be anything, right? So if I have the log base b of 1, right? So this is essentially b to what power gives me 1? And it's always going to give me 0, right? Because if I wrote this as exponential form, it would be b to the 0 equals 1. Now it doesn't matter if this is log base 7, log base a half, as long as it's a positive base. So it doesn't matter if I have a 1 here. The only thing it could be is this to the 0 power, because that is always 1. Okay, so that's rule number 1. And if I wanted to use the natural log, it would look like the natural log of 1 is 0. Okay, same thing. It just looks different. Log base b, I wouldn't even have the b if it was log base 10, but it doesn't matter what the base is. It's 1, and this would be base e. It just looks a little different because we call that ln, or the natural log. So the natural log of 1 is 0. All right, so next one, the log base b of b. Okay, so this is literally asking me b to what gives me b, right? So this is like b to the first, right? So this is actually equal to 1. So no matter what this is, right, if I have, for instance, an example would be if I had the log of 10. I'm not writing the base, but I'm assuming I'm in base 10 because it's not written, so this would be 1, because it's base 10 and 10 is in here. So this is like 10 to the first equals 10, which makes sense, right? I hope. So it would look like over here, the natural log of e is 1, right? Because this is base e, this matches it, so it would be 1. Alright, so another rule that we have is if we have log base b to the bx, this is equal to x. And what it looks over here is the natural log of e to the x equals x. Okay? So this is like saying if I had the log base 2 of 2 cubed, right? This question is literally asking me 2 to what power would give me 2 to the third? Well, of course, 3. It really is the exponent. It's like if I put it back in exponential function notation, it would be 2 cubed equals 2 cubed, right? So if I have something raised to the same base as my base is in, right, then I can do it this way. I can also think of it like this. If I had the log of 100, right, I know that 100 is a power of 10, so I could think of it as the log of 10 squared, and then in this case I could just apply my rule then. It's 2. So the same goes for natural log. If I have the natural log of e squared, this is just 2. Okay? Alright, so then one more of the simple ones, and it kind of is basically just slightly different than this one. If I have b, so if I have a log base b of b to a power, it's just the power. Also I have a b to the log base b of x. This is also just x. And over here this would be e to the natural log of x. This is also x. Okay? So for instance, if I had 2 to the log base 2 of x, this would just be x. Okay? Alright, so those are our most basic ones. So now we're going to learn a few more that are a little bit more complicated. This one kind of has a familiar name to it, but it's in context of logs this time. It's called the power rule. Actually, we're gonna start with the product rule. I got ahead of myself a little bit here. The product rule, but this one's for logs, not derivatives. Okay? So I'm gonna do a baby proof here, but so the product rule says if I have the log base b of 2 things that are multiplied in here, then this is equal to the sum of them. Log base b of n. Okay, so this is kind of if you think of it in terms of if I had a x squared and x to the fourth, right, and I was going to multiply them together, the logs are just the exponents. So if I have the same base, which that's what the log base b means, and I multiply that to two of the same bases together, then what I end up doing is adding the exponents, right? This would be x to the sixth. So this is just like the exponent part. So if I have two things multiplied together, I can just add them together. So I'm going to just do a little proof here, and it goes like this. So I'm first going to call little m log base b of big M. I'm going to call little n log base b of big N. Okay, so I'm going to put it in this form. So I'm going to say, okay, what's the log base b of m n? I want to write this in a different way. Okay, so I can actually change these equations that I started with, because I could write them in exponential form, which would be b to the m equals big M, b to the little m equals big M, and over here it would be b to the little n equals big N. Okay, so instead of m and n, I'm going to replace them. I'm going to replace m with b to the m. So I have the log base b of b to the m times, because I have multiplication, n is b to the n. All right. So now I have the same base that I'm multiplying together, and just like up here, right, when I multiplied these two things together, I added their exponents. So this would be log base b to the, or of b to the m plus n. And now we have that other rule that we just learned that was on the other page that essentially said, right, so now if we have this, log base b of b to the x equals x, I have the same thing here. I have log base b of b to the m plus m, so this is just equal to m plus n. So now I have, I'm going to bring this down, b of m times n is equal to little m plus n. And it just so happens, remember up here, little m was log base b of n, little n was log base b of n, and I have it. So log base b of m n times n equals the log base b of m plus the log base b of n. Okay? So that is just a proof of the product rule. So what that tells me essentially is if I would happen to have, let's say, the log base 3 of 9 times x plus 2, right, and that's all in here, and I could expand that and say, okay, this is the log base 3 of 9, because this times this, right? And then plus the log base 3 of x plus 2. So I can simplify this one more step, because I know that this 9 is also a power of 3, so I could rewrite this as log base 3 squared plus this. And I can apply that other rule again, so this is just now 2 plus the log base 3 of x plus 2. So when we get to the calculus part and some other things, we are going to use this in both directions. Sometimes we want to expand them and stretch them out, and then sometimes we're given something like this and we want to put them back like this, right? So it just depends upon what we're doing, but we need them in both directions. So for instance, if I had the log of x plus the log of y, and I wanted to shrink them together, condense them, because I have the same bases and there's a plus between them, I could combine them into one base. Okay, so it depends on which way we're going. So that is the product rule. Alright, so we also have another rule that sounds kind of familiar, but again, it's different. The quotient rule, but this one again for logs. And this one can be proved just like the product rule, but I'm not gonna prove it this time. But if you want to see the proof, please come in and talk to me. I would love to show you. I have the log base m over n, and this can be any base b, right? And this is the log base b of m minus the log base b of n. And that's because, like, if I have x to the fourth divided by x, then really this is x to the 4 minus 1, right? Because one of these would simplify. And so this is the same thing. I have the same base. I'm dividing, and so my exponents get subtracted. Okay. All right, so just a kind of a quick example using that. If I had, for instance, the log of, we'll just say 4xy over z, we can combine a couple rules here. So the first thing I kind of see is I have a quotient, so I'm going to write the log of 4xy minus the log of z. And now I also have a product in here, so if I wanted to expand it all the way, I have this times this times this, so I could say the log of 4 plus the log of x plus the log of y minus the log of z. So it's maximum expansion, right? I have these multiplied together, so they end up as pluses, and this one is in the denominator, so it ends up getting subtracted. All right, so there's one more rule that we're going to talk about, and that is the power rule for logs, right? These all sound very familiar, except for this time we're dealing with logs. And this is how do we deal with things with an exponent. And this is this is a big reason why we like logs. If I have log base b, and I have, for instance, x squared, let me just talk about this for a second. We can think of this, right? X squared is a product, so I could just think of this as log base b of x times x, and use my product rule, which says I have log base b of x plus log base b of x. And really, these are the same things. It's just like x and x, and when I have x plus x, I have two of them, so this would be 2 log base b of x. Okay? And so that we can generalize that for all. So basically, if I have the log base b of m to the n power, then we can write this as n times the log base b of m. Okay? So, for instance, let's just do another simple one. If I have the log of x to the 4th, then I can write this as 4 log of x. Now, I do need to be a little bit careful. So if I have the log of x to the 4th times y, then I need to break these apart before I bring the 4 down, because the 4 only applies to the y, or to the x, and not the y. So I would first want to write this as a product, and then in my last step bring the 4 in front. So this is 4 log of x plus log of y, and that's its full expansion. Alright, so those are our 3 basic, or the bigger rules. And so in the next lecture, we're going to do some expanding and shrinking of some more difficult ones.